Our next plenary speaker is Jayshree Ullal. She's the President and Chief Executive Officer of Arista Network, a role she has held for the past decade. She led the company to a very successful IPO in 2014 and to $4.4 billion in revenue last year. Formerly, Jayshree was the Senior Vice President of Cisco, responsible for a $10 billion data center switching and services business. With more than 30 years of networking experience, she is the recipient of numerous awards, including Ernst & Young's Entrepreneur of the Year in 2015, Barron's World's Best CEOs in 2018, and one of Fortune's top 20 business persons in 2019. Earlier this year, Jayshree was awarded a Global Indian Award from the Economic Times of India. Jayshree holds a BS in Electrical Engineering and an MS in Engineering Management. She is the recipient of San Francisco State University and Santa Clara University Distinguished Alumni Awards in 2013 and 2016, respectively. In the next 30 minutes, Jayshree will discuss the road to PetaScale Cloud Networking. Please join me in welcoming Jayshree.
Good morning, everybody. Wow, thank you for that introduction, Chris. And how inspiring to see all of the awards and optical expertise. I think you've all forgotten more than I can ever speak on that topic. But it's great to be here, and it's especially great to be here, post the COVID era. We all have a lot of fatigue doing collaboration, and much as it's been powerful, perhaps touching and seeing and really, really connecting with everything we do is one of the greatest parts of the Optical Fiber Conference. Today I'm going to share with you some of my experiences and technologies, and especially represent Arista on our path to petascale networking. It, of course, has a high touch of optical, but it has many other components that one has to think about before we even get to the optical piece of it. So I'll talk a little bit about Arista. I know Chris gave a warm introduction. It's been one of the fastest growing companies that I got a chance to be part of with Andy Bechtolsheim, our founder, and Ken Duda, right from the ground up when we were zero. We'll talk about some of the trends that made Arista happen with cloud, and today a greater trend that's emerging with cloud scale, and the path to petascale and what's required to make that happen. Bandwidth is one thing, but the pressure to attack that bandwidth with the right latency, predictability, throughput, lossless network is very key. And finally, of course, the reason we're all here, we'll talk about the O in optical and wrap up after that. All in 30 minutes at peta speeds, obviously. Let's go back again now to the 1990s. Now, you heard I have a career that goes back. Wendell and I were talking yesterday. We go back a few years. We now measure our career in decades, not just in years. So we therefore get to be historians and talk about the past more than we do often the present and the future. And so looking back in the past, I want to compare how networking has evolved the way desktops have evolved. Many of you may remember we all used to sometimes even build our own desktops, whether it was a Radio Shack or a Compaq, and now we all pretty much buy them off the shelf. It's a consolidating industry where you don't worry about the disk drive or the graphic controllers or the display or the screen. You just build a whole system. And you heard Patricia talk about the systems and the impact of that in every country, in every individual, in every girl, and every person. Today also, we've gone from a myriad of operating system choices, whether it was Windows or Solaris, and I'd be dating myself if I went back to the DEC and the VAX clusters. And today, again, you've come to a consolidated OS that's largely based on Linux or based on Unix. And then in the past, you also had different types of desktops for consumers, for enterprise. And this world is collapsing as well to a multi-cloud era, where all of these, in essence, become an extension of the cloud, whether they are mobile devices or iPads or large systems. I believe in the 2020s, the networking industry has and is going through that kind of consolidation, where you now have to worry about the traffic, not just north, south, east, west, but really 360 degrees. And we are building massively large networks what we call a leaf and a spine topology, to deal with this traffic. And often it has to be built in tiers, whether it's 10 gig, 40 gig, 100 gig, 200 gig, 400 gig, 800 and 1.6 terabit. That traffic pattern requires you to deal with active-active topologies, the ability to take traffic across IP, across Ethernet, across optical, and build an N-way spine, a multi-way spine, and connect to it different kinds of leaves, as we call them. And these leaves power our different applications. It could be compute, storage, private or hybrid cloud, Web 2.0, 3.0, campus branch, and two especially ones that are pressuring the network even more and more today are the cloud and the AI and ML workloads that go with that, as well as, of course, the optical interconnects that go with that. We work with some of the largest cloud titans in the world, or hyperscalers. And you know there's only a handful of them. And yet they are pushing not only bandwidth, but a very important topic today, which is the power efficiency. They're building some of the world's largest global data centers that are hundreds of megawatts, sometimes gigawatts and terawatts. And they build them in distributed centers. And I often like to say, it's not that they just build data centers, they build centers of data. And that center of data could be a large megawatt where they build multiple racks of pods and spines and distribute the traffic regionally, or it could be even a small branch. And so the power of data across these centers is what the clouds are making possible for each and every one of us. Arista has actually emerged as one of the leaders and probably one of the fastest growing companies in this high-performance networking sector. And you can see here an independent data from a market analyst that shows that just in 100, 200, and 400 gig alone, Arista is now the largest market share in ports at over 40%. And still, of course, we're competing with some large juggernauts and some of my ex-industry peers. And so we all have a lot to do here and a lot to go. One of the things that makes that possible is the silicon industry. You all know that Moore's law is very alive and well. And the geometry of transistors has been literally doubling every 2 years and growing from 100 nanometers to today in the 2021, 22, 23 era, we're down to 7, 5, and 3 nanometer. And the transistors have grown from a few 100,000 to millions and billions. This makes possible a number of electrical switches and high bandwidth that Arista and many companies can take advantage of to get the electrical part of our switching right. We've gone now from 25 terabit SerDes to 50 terabit capacity, moving on to hundreds of terabits. And this is possible because of the geometry of using merchant silicon to really make this happen. But I'm here to tell you that we are going to push the envelope of electrical and very soon optical even more with the next workload that gets on the cloud, which is artificial intelligence. Sometimes I think the word AI gets misused, and perhaps we should rename it RI and call it real intelligence, because there are so many emerging applications now in our daily lives to make this possible. The large-scale ML has exceeded any forecast imaginable. Natural language models are now going from the billions of parameters to 1 trillion parameters. Early results have been very, very impressive. Google Lambda, the Megatron, the Bloom, all of these are pushing the envelope, and they're really coming out of the labs of neural nets to become real applications that affect our daily lives for recommendation engines, training engines, inference engines. And these AI ML clusters don't necessarily first start with a network, they start with processors. A special kind of high-end going beyond general processors to GPUs that have anywhere from hundreds to thousands to 10,000 GPUs that generate a tremendous amount of bandwidth. And therefore, networking bandwidth to connect all of this I/O is a very limiting factor. Targeting these AI ML clusters in the future, therefore, requires terabits of GPU capacity to build petascale networks. And we'll talk a little bit more about how that's built. First, to build these GPUs, you need servers. And these aren't often general-purpose servers, but they're actually very specialized servers. As an example, Facebook Meta most recent server announcement was based on a 8 cluster of H100 NVIDIA GPU platforms. And this is an AI ML chassis with multi-terabits, gigabits, petabits that have to connect all of these 400 and 800 gig slots. NVIDIA's DGX is one of the most popular ones that has 8 A100 GPUs and was announced back in May 2020. These are examples of very, very high-end servers powering and clustering the AI ML workloads. Another example would be Google's TPUs, TensorFlow processors as they're called. And you can see here that every year the TPUs have exceeded the chip density and also gone from petaflops to exaflops, 10x almost every 2 years, a combination of both faster chips and very large clusters. And the prediction in 23 is you can go from an exaflop to 10 exaflops. So it's just getting faster and faster and denser and denser. The large language models that sit on these GPUs is a huge consideration. ChatGPT, which has been one of the rages and apparently hit 1 million users in just 5 days, is already training 175 billion parameters. Megatron natural language models are over 500 billion, 500 billion, sorry, models. And it's trending to go to 1 trillion models in the future. AI models are touching our human lives as well, whether it's marketing content, speech, advertising, video, 3D, imaging, code. It's now not just back in the labs. Just about every aspect of what we do is being powered by AI. Now, what does this all mean? Why are we discussing AI so much? Because it is both compute and data intensive. If you look at a typical AI-driven sparse matrix, you run the data across billions of parameters, and then you do a whole gather, search, reduce, and you share all of the adjustments across the parameters simultaneously. And then you update all of the parameters globally every step of the way. This process of compute, reduce, exchange across the peers is very data and compute intensive and happens repeatedly in what's called a data parallel training for different kinds of traffic patterns. You're going back and forth, shuffling over and over again. Not only do your GPUs need to respond, but the I/O has to have an immediate response. It cannot have idle states. The GPUs can't be waiting for it because that's precious time, precious latency that you're using for it. So this typical structure of a distributed AI therefore requires something much more than we have today. You add to this the fact that your parameters are going 10x, and then on top of that, the features required are going 40x. You need bigger models, bigger GPUs, and larger networks. AI networking promises to be far greater than what we have already deployed for today's cloud and optical networking. And so if you step back and look at some of the attributes you need to be able to do that, the first thing you need is not only to be able to go fast, but to go predictably, without loss, without congestion. A lossless fabric to deal with the many forms of AI communication and yet handle it gracefully without dropping packets. Whether you have large flows, elephant flows, you've got to synchronize all of these packets to make it run smoothly. Just fast lanes isn't good enough. Predictable lanes is extremely important. You also need to move more and more to state-of-the-art technologies, the IP, the state-of-the-art Ethernet, and be able to do reliable transfers, not just across the transport protocol, but also have the right restartability, resiliency, availability, because when things fail, they fail very long and create billions of dollars of outages. So the benefit of combining standards-based protocols so that you have the right resilience, active-active, one goes, the other comes, and it comes up fast is extremely important in real time. And finally, visibility and telemetry. You can have a fast network, and yet you can have a choking point. And to identify those applications at the application level, at the network level, at the path level, at the protocol level, at the DWDM level, at the optical level, is critical to building a holistic network. One of the key reasons that this is so important is you've got to build the right foundation. You can have all of the architectural principles, but if you don't have the right architecture, then you won't be able to get there. So a couple of key things in the architecture required is a non-blocking, high-performance, terabit scale going to petabit scale network. You've got to make sure it's no drop. A virtual output queuing architecture allows you to, at both the ingress and the egress, deliver these packets at fast speed, but also make sure they're not collision-free. You've got to have a proven transport architecture that can not only go direct memory across different transports, but also be able to respond to that transport with deep buffers to reduce the pause, the congestion, per flow control, explicit congestion control. The combination of all these means it's not just about bandwidth, it's about synchronized flows. It's just not about packet latency, it's about your entire end-to-end workload latency. A lossless network matters. The optical internet connecting to that network matters even more. You also need to think more about the software features and make sure they're more programmable at the data plane, management plane, control plane. You have to have extensive monitoring so that you can look at what's going on at every microsecond interval, every nanosecond interval. The right debuggability, flow tracing capability, the aggregate of counters and monitors, the real-time streaming of telemetry makes the software as important, embedded, and infused into the hardware as the architecture itself. This is an example of a real-world AI spine that Arista has constructed. And you can see here, very often, everyone's well known for the front end of the network, where you're connecting a large amount of 400 gigabits across a leaf spine architecture and building what I'd call the data center cloud network. But for every front-end network, there's also a back-end network. And these back-end networks typically used to be connected with CPU storage, often serial ATAs, PCIX, et cetera. But now, increasingly, for these AI-intensive workloads, you need a dedicated back-end AI spine that goes beyond the compute and memory clusters to build an equivalent network like you did in the front end. Now, how do you build this network? Well, clearly, they come in different sizes and different shapes, depending on what you're trying to do. So let's take a look. For example, if you're just within a server, like I showed you, you don't need a lot. You need the I/O to go very, very fast across, let's say, 10 to 100 XPUs. They could be GPUs, TPUs, et cetera. And the type of apps you're dealing with here are more small, simple. And your AI options here, in terms of network, may not be a network at all. It could be a simple I/O connection like PCIe or CXL or NVIDIA's NVLink. So this allows you to just sort of pass back and forth in a bus type of topology, and you're not really getting out of the server chassis, if you will. If you start getting out of the server chassis, then you need a rack scale or a pod scale. And this is where the leaf spine topology really shines, where you may have an InfiniBand type of network for high-performance compute, or you may have an Ethernet network, especially as InfiniBand and Ethernet are approaching the same speed and becoming more and more at heavy workloads, predictable in latency in a similar fashion. You would typically apply this over moderate applications, where you're getting out of the chassis, out of the server compute, and starting to put racks and racks of compute and build multiple pods, if you will, connecting into a spine. And finally, the picture I showed you before, the AI spine. This is when you start worrying about the billions of parameters, the trillions of parameters, and you need a data center scale that connects not just thousands of GPUs, but 10,000 or 100,000 GPUs. Everything from how you cool it, how you connect it, how you immerse it, how you design it is non-trivial, because you're now creating the supercomputer in a completely distributed fashion for a new generation of AI loads. And these are typically, therefore, powered by large AI apps and must, therefore, have a real network with Ethernet and IP powering it. And this is a lot of what the next generation designs and the next generation cloud providers are trying to build. So if you took away anything today in the last few minutes, dense processors, fast networking, and optical is a must. Today's GPUs can drive roughly 2 times 400 gig, going to 800 gig. And a 10,000 GPU network, like I showed you in the AI spine case, can use as much as 8 petabits today and demands that much of non-blocking bandwidth. Insufficient networking bandwidth can be a real problem. Imagine I have these expensive GPUs that can be worth hundreds of millions of dollars, and I'm going back and forth with data cycles, crunching the data, and if I have a 30% wait cycle, that means out of those hundreds of millions of dollars, a third of it is wasted. So getting the right network foundation, a faster, seamless, predictable, lossless, congestion-free network, not only requires a network, but also requires, and here we are at OFC, an improved optical interconnect. It's so interesting to watch that although we talk about bandwidth and performance, the largest contributor to power in a data center is not the network or the merchant silicon chip that the network is built on, but the optics. You can see here in the pie chart, in a 100 gigabit network, the optics is easily 35 to 40% of it. You go up to 400 gig, it's fast approaching 50. You go to 800, you're more than that, 55, 60%. And therefore, you need more fans to cool all of that as well. So how do we build, for all of these AI workloads, a power-efficient optical network? This imperative is why we're all here gathered at this conference and at this plenary, and I want to share with you different ways we can think of this problem. Obviously, you all know that in an AI network, we have a switch chip, but we also have the photonics. And the photonics has two components. You can have an electrical component, and you have to be electrically efficient. And this is the power of E. The E contributes power, which can be the switch chip, the retimers, the DSPs, et cetera. Or you can be optically efficient and reduce the power there, which is reduce the power through the laser efficiency, the modulators, the switch voltage, insertion loss, et cetera. Let's talk about the electrical efficiency first. Many of you know and have been working on the co-packaged optics. This is a dramatic way to reduce the power efficiency by bringing the electrical and the photonics closer together. And making sure the advantages of this is you bring the power to a lower piece, you increase the performance across the I/O, and of course, by definition, you have lower costs because you don't have two packages. There are some challenges in terms of reliability, efficiency, pragmatic, practical challenges as you deploy thousands of these. How do you manufacture them? How do you service them? How do you return them back to factory? That are still being solved. But nevertheless, this is a very powerful way to reduce power. On the optical side, there are more powerful ways emerging as well, by actually changing the materials. TFLN, thin film lithium niobate, as I understood it to be. My husband worked in the thin film industry many years ago, and I never knew it would come back here again as photonics, can reduce the power of the O, where by coupling the laser efficiency, coupling efficiency modulators on a thin film material, you can now dramatically reduce the power. Now, we are demonstrating we have demonstrated the use of DSP and thin film lithium niobate technology last year, and you'll see it again in our labs today in the booth. But what would be the ideal power reduction is if you could bring the best of both. Bring that signal integrity on both the electrical side and the optical side. And bringing that electrical and optical efficiency comes from removing the DSP completely and directly connecting the switch chip and the SerDes to the photonics. And now you get the best of both worlds. You get the lower power, you get the lower latency, you get the lower cost, combined with no trade-off on reliability, manufacturability, or serviceability. This is what we call linear drive optics. And it's one of the most exciting introductions that the industry and my team and all of the teams have pioneered. You'll see that today, and where you're now no more making the trade-off, and you're getting a tremendous advantage in power. There are many materials, by the way, that can make linear drive possible, not just TFLN, but this can run with silicon photonics and VCSELs as well. But the beauty of this is now pluggable optics can take you to the next generation of high bandwidth and low power. You can see here in this chart how with different switch silicons at 51 terabits and 100 terabits, at a system level, you can get a dramatic power reduction greater than 25% when you bring the switch, the fans, the CPU complex, and the optics using LD. LD and pluggable optics is a real revolutionary advantage now, because you can get the bandwidth and capacity and throughput and not have the massive power ingestion that we've all been experiencing. I've been sharing a lot with you right now on the theory of all the things we can do. But it would be great to see a technology demonstration, so let's take a look at a preview of how this happens in the labs.
Hello everyone, and welcome to Arista Labs. We're very excited to demonstrate a new class of optical transceivers that we've been optimizing over the last 3 years, which we call linear drive modules. Linear drives are optical pluggables that do not include a DSP, offering lower power, lower latency, higher reliability, and lower cost. With today's shipping 100 gig SerDes generation, we're measuring good bit error rate performance with floors reaching a few E-8 for the full E to O to E linear channel, as can be seen in a 25T system. Now, our industry really likes plug and play, with an open multi-vendor ecosystem that is interoperable. But this really means one thing: performance margin. With the latest 51T switch silicon that integrates full DSP capabilities with much improved equalization and much lower SNR sensitivity, we're happy to report a 3 order of magnitude improvement in terms of bit error rate floor. With the latest SerDes generation, we're demonstrating a linear drive optical interconnect using 2 optimized modules sitting on the edge ports of this 51T switch. We're measuring excellent performance after 10 kilometers of single mode fiber with prefect bit error rates reading a few E-8 and a few E-11, well within the KP4 FEC limit. If you'd like to learn more about linear drive modules, please make sure to stop by Arista booth number 5401. Thank you.
Well, I want to especially thank Hassine and Andy Bechtolsheim for that demonstration in our lab. You could hear the fans and you could hear all the cooling that was going on in the lab there. And it's just fantastic to see these eye patterns with the right bit error rate. We have clearly entered the golden age of PetaScale. I hope you share with me the excitement and enthusiasm of bringing next-generation processors, next-generation AI apps, into an amazing foundation for a PetaScale AI-based network with the right power-efficient interconnect. I'm excited to have been able to share this with you, and thank you for this opportunity.
Thank you, Jayshree.